Excellent. Okay, very good. Good morning or good afternoon or good evening, wherever you are, and welcome to our Physical Review Fluids Journal Club. I'm Eckart Meiburg from UCSB. And before we get started, I would like to ask you to please mute yourself and also turn off your camera so that we can save on the bandwidth. So a little over 2 years ago, Tom Peacock and Thierry Dossois organized a wonderful workshop at beautiful Les Ouches near Mont Blanc in the French Alps on the topic of grand challenges in environmental fluid mechanics. And I had the good fortune to participate there, so it was a really very enjoyable event. The workshop covered a very broad range of topics, and with the help, please mute yourself. And with the help of the workshop participants, Tom and Thierry subsequently created an overview paper that highlights many of the outstanding problems in environmental fluid mechanics. This paper is the topic of today's journal club. So at this point, I would like to introduce Tom Peacock, who will take the lead, and he will provide an overview over the workshop. And then several of the co-authors of the survey paper will give more specialized presentations on their parts. So Tom Peacock is a professor at MIT in mechanical engineering, and he's also the director of the Environmental Fluid Mechanics Lab. Tom has done groundbreaking work on stratified flows, on internal waves, and many other interesting topics. And in particular, in recent years, his research interest has focused on deep sea mining. In fact, just a few weeks ago, Tom returned from a 6 or 7 week cruise in the Pacific, where he and his team performed field research in order to assess the environmental impact of deep sea mining operations. Tom, we're very happy to have you present the overview of the paper today, and then to coordinate among your co-authors. Let me just mention one more thing. If you have any questions, please use the chat function, or after the presentation is over, you can ask your questions in person. Okay, please go ahead, Tom.
Great, thank you very much, Eckart. I will claim the screen sharing from you, if I may. And thanks to everyone also for making time to come and hear our presentation. So I'll just give a brief overview, and I will also organize the slides of my colleagues who are presenting today. So hopefully you can see this is a snapshot of the article that appeared. We're very grateful, very thankful for PRF for both hosting the article, but also giving us this opportunity to talk about the work. So as Eckart said, this stems from a workshop, and the sort of philosophy behind the workshop is that, with all the climate challenges, the challenges facing society today, we really wanted to call out that environmental fluid mechanics actually underlies a lot of the challenges that society is facing. Obviously, not all of them, but for example, problems on the very fundamental side, such as modeling of fluid flows, stratified turbulence, and mixing, as you'll see, play a very big role in grand challenge problems such as climate and weather modeling and urban environment design, and very applied studies. You can have an oil spill in the ocean, microplastics in the ocean. These are very applied problems where the underpinnings are fluid mechanics. So our message of the workshop was to pick 5 key focus areas. So you will hear about them. We have presentations on multi-phase flow, stratified flow, ocean transport, atmospheric urban transport, and weather and climate prediction. And here's a quick picture from the workshop. When we were able to meet and have these gatherings back in 2019, and hopefully this will all be the norm again soon. I will particularly call out a thank you to Thierry Duxoir at the front here, my co-organizer of the workshop, who really helped make this happen and pull it together. The article very much too as well. He helped lead that. And so throughout the talks, you'll see that everyone is relating their research to the UN Sustainable Development Goals. So I've circled a few here just as examples. So for example, of the 17 goals, item 3, good health and well-being. Well, of course, in the past 18 months with COVID, we all understand how the fluid dynamics of airborne transport of disease is right at the heart of solving one of society's greatest grand challenges. And you don't have to stretch your mind far for thinking in terms of life below water and climate action, where fluid mechanics lies there. So that's a real theme. I think with this article, we want to call out to researchers in environmental fluid mechanics to engage with policymakers, decision makers, etc., and use science to underpin these very important decisions that have to be made in the coming years. So I'll wrap up quickly by thanking everyone who helped make this article happen. The staff at the Les Houches facility that facilitated the meeting. There's financial support from CNRS, from ANS de Lyon, IDEX Lyon, and the MIT Environmental Solutions Initiative. And if you're interested in any aspect of the presentations today and want to go in a bit more depth, all the presentations from the meeting, all the research presentations are available at the web link here. And I believe this presentation is being posted on YouTube. So if you don't grab it quickly now, you can go to YouTube and get it, and you can see any of the talks. So with that, I will wrap up my introduction, and I will then introduce the first speaker. So Nathalie Vriend from Cambridge University presented work on multi-phase flows with Eckart Meiburg, who co-authored the article. So Nathalie, I will hand over to you, and thank you very much, everyone. Nathalie, over to you.
All right, thank you, Tom. So indeed, I would like to introduce one of the 5 topics of the conference, and this one is focused on multi-phase flow. So to start off, if you focus your attention to the top left corner, you see a cloud where we have a gaseous phase. Out of the clouds you could get rain, which is liquid, but also snow, which has some solid properties. So multi-phase flows kind of relate to the different phases and also the transformation between phases that a fluid can take. And if we look at the volcano on the right-hand side, you see an example of a multi-phase flow in the environment where we have a mud flow forming coming down a volcano. And there you can kind of get an idea on what the challenges are if we're looking at scales. So we may have these mud particles at the micro scale or the millimeter scale on a large volcano, which even has an ash cloud above it, which can go over hundreds of kilometers. So we have a massive discrepancy in scales here. And a third complication that you see in multi-phase flows in the environment, which can happen in the atmosphere, land, or water, is that we're looking at a very complex rheology. This is not a simple Newtonian flow. Because of the interaction between particles and fluids, we really are looking at non-Newtonian or complex rheologies that we need in order to describe flows like this. So next slide, please. So multi-phase flows can be natural or man-made, and we see the example of deep sea mining in the top left. And even if they're natural, like for example, the melting of sea ice, we're always wondering what's the feedback between processes. We have the melting of a solid. Does it actually impact the fluid, the environmental properties, and how does it impact back to the melting? Another example is, for example, the intake of carbon dioxide in our oceans. And there's actually, it's a very sensitive process. There's a lot of uncertainty if we think about carbon dioxide and the multi-phase components of that in climate modeling. And a last example of the motivation is on the bottom right, you see a so-called dust storm or haboob. where we have solid particles, sand, dust being whipped up in the atmosphere and are engulfing agriculture and fertile land. And that has a direct impact on the livelihoods and the well-being of the people that are living there. And it impacts people directly. So that kind of highlights the impact of these multi-phase processes. Next slide, please. To kind of put the same, no, one back, please. Thank you. So to highlight these pictures that I just presented to you, they're actually impacting the Sustainable Development Goals directly as well. And I just give you some examples of life below water and climate action, where we have the fluid phase of oceans or lakes. But we're also thinking about melting of sea ice, where we have a great loss of fresh water and clean water. And the last example on the bottom right is Habub that I introduced. It has a direct effect on life on land, healthy agriculture, and it creates hunger as well. If we have desertification and you know, more arid lands being created by these dust storms. Next slide, please. So when Eckart and I started to write this article, we actually split it up in two different parts because that came most natural to us. So the first part is dry multiphase flows. And I am presenting an example here from our lab where we see these photoelastic grains running down an avalanche, running down a base. And this is our 2D representation of a dry multiphase particulate flow. And as you can see, we see these individual particles, and the collisions are very, very important here. So the particle interactions are dominating our processes. In this case, we don't have any we don't have any fluid in between the particles. If there is, if it's just playing a minor role, we don't have to worry too much about it. And it's really the collisions that play a role in these dry multiphase flows. Then if you think about the breadth of problems that we can look at and the methods that we can look at, it's, for example, the discrete particle modeling, where we have Newton's equations of motions, and then we can follow the tracks of the individual particles. Another approach is to look at it from a more stand-back point of view. If you do continuum modeling, we can still model these granular flows, but we need a constitutive model that represents the physics accurately. And there's actually a lot of development as well on more the modeling or the experimentation, both laboratory and field experimentations. But the complicating thing with granular flows is that if you take a particle and you move it to another location, the outcome can be very different. So next slide, please. The second focus was actually on wet granular flows. And we see here an example from a research paper coming from Eckart's group by Voewinkel. And this is settling of a particle phase in a fluid. And it becomes even more complicated because at the top here, you see a very dilute phase where the particles are directly interacting with the fluid. And as these particles settle down, they actually compress and actually form, if you could check whether you're muted, please. So as the particles settle down, you can see a very dense phase at the bottom. So here, if you think about particle interaction, it's definitely dominant in this dense phase, but even in the dilute phase, there may be still a minor role for particle interactions. But if the fluid is there, we have additional fluid forces like viscous forces, buoyancy forces, pressure forces. If we look at the tools that we have to characterize these wet multiphase flows, we can think about continuum modeling using the Navier-Stokes-Boussinesq equations, where we take the packing fraction and the density into account. We can also do, again, grain resolving simulations, and a method that's really gaining popularity recently is the Immersed boundary method, where you're kind of modeling a particle and its impact on the fluid and the feedback between the two phases. And looking at the theoretical modeling, there's actually a lot of semi-empirical work. It's tricky because we're depending a lot on measurements, and experiments in fluids are just adding complexity and variation and uncertainty. Next slide, please. Last slide, actually. So if you think about the perspectives, we're actually in a very exciting time now. We have innovation in experimentation, where we have drones flying on Mars, getting interesting field data. We have laboratory experiments. These are high-speed cameras that are giving us unprecedented resolution in both spatial and temporal phase. So that's really exciting. We're also seeing a great improvement in our computational powers, where we have the large supercomputers that allow us to upscale our tools and simulate larger systems. And of course, if we have these bigger data sets, whether it's experimental or numerical, we always need to make sense of these data sets. And now with machine learning, we can really kind of get a good handle of it and make sense of the large amount of data that we're able to collect. So that's the end of the multi-phase flow part. I'll give it back to Tom.
Great, thanks very much, Nathalie. So then the next talk in the theme of the meeting is on stratified flows, and this was written by Colm Caulfield and Greg Ivey, and Colm is going to present on this today. So Colm, I will hand over to you.
Thank you very much, Tom, and thanks to the organizers of this wonderful week up the mountains. And also I'd like to do a big thank you to both Greg Ivey and Matthew Alford, because we talked about the stratified mixing type problem. So next slide, please. So why should we care about stratified mixing? Well, because the oceans and the atmospheres indeed are stratified, and vast amounts of heat are transported around within the ocean by the interesting currents, like you see on the left there from Kathleen Doan. And the amount of heat is gigantic. It's about orders of petawatts that are poleward heat transport in the oceans. And a key component of that process is actually deep mixing, which is the beautiful picture you see on the right from Waterhouse et al. 2016, where you can detect a kilometer above the bottom of the ocean, whether the bottom of the ocean is with the topography underneath, which is about the internal waves are transporting energy non-locally, the waves are breaking through turbulent processes and having enhanced dissipation. So you really want to understand how heat is being transported in the ocean, because, next slide, Tom, because of course, the global climate system is heating up in a very worrying fashion. It was indeed quite interesting. I went to the Guardian newspaper the first 2 weeks before the meeting in 2019 and had these scary pictures of the fact that the ocean is really heating up quite significantly, measurably, and that is very, very concerning, as indeed the very strange weather we're having at the moment, the extreme events. Those can be associated with the fact that you're changing the boundary conditions of your system because you're heating up the oceans, and so the atmosphere is being modified. And so in terms of those sustainable development goals, next slide please, Tom, there are major ways that understanding how heat is transported in the ocean is clearly as important to climate action. It's clearly important for life below water, but it's also, because of the tendency to trigger perhaps extreme events, significant for the sustainability of cities, particularly in coastal regions, and access to clean water and sanitation. It is a major, major concern for understanding sustainable life on this planet to understand how heat is transported in the deep ocean. So how do we know about that? Next slide, Tom. The fundamental idea to understand is that when you have a stratified fluid that has turbulence in it, there's an extra energy sink within the system, because if you have turbulence and mixes a fluid up that's dense near the bottom, lighter higher up, that mixing of fluid inevitably increases the potential energy of the system. So effectively, stratification taxes turbulence. There's another sink, not just the viscous dissipation, there's another sink to do with density flux or buoyancy flux in the vertical direction. And understanding that partitioning between the buoyancy flux, that G over O naught W prime rho prime, relative to the buoyancy frequency, the natural oscillation of a parcel of fluid in a dense stratification, this n squared, understanding that parameterization in terms of that eddy diffusivity is a key problem for these larger scale models. And understanding how that works is about how you partition the buoyancy flux B compared to the turbulent dissipation epsilon, so this particular quantity gamma that my assistant is circling beautifully. And the question is, what parameters does this depend on? Because there's a whole slew of different parameters you could have in the system. There's the property of the fluid, the Prandtl number. There's the Richardson number, the ratio of this buoyancy frequency to a shear within the system, which is an energetic balance. You have a turbulent Vriend number, the relationship between epsilon n and the kinetic energy density k, or the buoyancy Reynolds number, which can be thought of as a ratio of length scales or time scales between the intensity that you have in the turbulence. So that's really the problem. It's just maths, scary maths. You've got to understand how you manage to partition, how you could use the parameterization, and you face a horrible problem, which is the more realistic the flow you consider, the worse the quality and quantity of data available. So just like that beautiful thing that Nathalie said at the end, you want to have an interaction between high quality simulation experimentation, observations, and modeling parameterization. The problem is you are on a trajectory from the more idealized the situation you have, you've got good data, but if you want to apply to the real world, you have much rougher quality data. So that's a real challenge. And so rather, like I said, we don't even know what we don't know. There's really three fundamental things that are still completely outstanding that we don't properly understand. So could I have the next slide, please? We don't understand spatiotemporal variability, because you can inevitably within these flows have instabilities. You can have like the Kelvin-Helmholtz instability of overturning of a weak stratification, but you can have other types of instabilities because you can also have very strong stratification with sharp interfaces, and then you have a different kind of instability that doesn't overturn, it just scours or just erodes a little bit, as you're shown in the top right picture. So you can have these long-lived, you can have instabilities with different timescales, and there is emergent evidence that sometimes actually they go towards a marginal stability case, that the flow is like it's like self-organized criticality, that you, as soon as you go slightly unstable, you mix the fluid up and then you turn back towards a stability, marginal stability. So understanding the oscillation in space and time is real challenge within these flows. But that's not the only challenge. Could we have the next slide, please? There's another challenge to do with length scales, because inevitably the process you have in a stratified flow of mixing fluid will mean that you'll end up with regions where the fluid is relatively well mixed, a layer, and then sharp interfaces where the density is very rapidly varying. And so hydrodynamically, you spontaneously form staircases. And so it's not even clear what the right value of a parameter is to choose, whether it is the bulk average or an average over a narrow area, over the interface, over the layer. It's very hard to tell. And you can then have competing length scales between the length scale of the stratification and the length scale of the turbulence or the overturning. And so I wonder, there seems to be emerging evidence again that fluids adjust to a kind of Goldilocks phase, neither too hot, where the turbulence is much smaller than the overturning scale, nor too cold, that the overturnings are very small and the turbulence scales are much bigger, but just in between. So that's one emergent thing that's coming through. Could I go to the next slide, please? And finally, another emergent thing is how important is the form of the forcing that you have. If the flow happens to be in a very force continually, you end up, once again, a concept of something emerges. The flow adjusts to a perfect balance between dissipation and mixing. But in other cases, like if you force with waves, you can once again spontaneously form layers, and you have once again a particular balance between the taxation rate, which is a different taxation rate, which is really rather curious. So we have these the problem's really important. We have these three different things we need to worry about. We need to worry about spatiotemporal variability, we need to worry about length scales, and we need to worry about the dependence on the forcing. So if we could go to the next slide, please, the last slide. So we really there's loads and loads of open questions. And so once again, just like Nathalie was saying, that there's a suggestion that since we can get some data, maybe it is better to use machine learning type approaches to understand what is actually happening, get to access all the data that you have available. And this nice thing from Miles Couchman, who's working with me and Matthew and Rich Kurzweil on looking at machine learning clustering analysis of observational data to identify different kinds of mixing events different places in the real flow. This is a flow off Palau, but there's some evidence emerging that this is actually kind of the way to go, physics informed, but use machine learning to really understand stratified mixing. So thank you for your attention. That's me done, Tom. Thank you.
Great, thank you so much, Colm. So then moving on, for the next topic in the paper, the focus is on ocean transport, and George Haller and Nadia Pinade gave the presentation at the meeting, and Nadia is here today to talk on that topic. So Nadia, I'll share your slides and over to you.
Thank you very much, Tom. So here we go in a field that is rather crucial in these years, that is fighting against pollution in the ocean, that is becoming a really serious issue, and that by 2025, unfortunately, it was thought to be decreased for both marine debris and nutrient pollution. In order to do that, we need to understand how tracer transport works in the ocean. Why am I saying the ocean? Because the ocean is a very particular turbulent, large-scale turbulent flow field, particularly large-scale turbulent, and with also all sorts of smaller scales and mixing processes occurring, but two-dimensional, quasi-two-dimensional turbulence in the ocean is particularly evident and present and pervading the flow field. So we need to know how this turbulent transport occurs. And I found myself, I learned from George Haller this new method to understand how these eddies with finite life, but they could be as long as years, are real actual barriers to diffusive tracer transport. And he has this new method, which I'll try to explain, but please refer to his paper that is written in, and partly the explanation in the paper, in the fluid paper, but also in others. And then I will show you part of my group work, which is going into discovering probability distributions for hazard mapping. You know, we suffer in oceanography from and hazard mapping for fluid flow transport from extreme non-generic approach. And so we thought several years ago that the correct approach would be to specify the correct probability distributions to be used. Okay, next please. So just to show you how barriers are evident in the ocean. You see here two wonderful images, one from satellites for chlorophyll, which is very, very common in the ocean and in the Barents Sea, and you can see many of them. You see a lot of structures, in fact, but you see a strong gradient. And then here you see it from our drifters. You see the drifter on the upper right corner of the image. The kind of drifter that we use is really the surface drifter. And then you see all the integrated pattern, but you see also around Florida, and you see also that there is a region where the drifters don't go. And so this is a barrier, and it's not topography only. It's partly, but not only. Okay, so George and his group, George Haller from ETH Zurich, next please, found, I would say, a real novel way to study the advection diffusion equation for a concentration, C, and to define a material surface. Hello? Yeah, a material surface that would be within a finite time a barrier to diffusion. So this material surface doesn't require to do a simulation of Lagrangian transport, for example, to be found, but it can be found by minimizing non-dimensional transport functional that is here defined. And you actually can find in George's webpage a lot of tools already available to open source to be used for your particular transport. Next, please. So the next important thing is that George has gone to real eddies. For example, we have satellite altimetry in the ocean, where we detect sea level anomalies, and these sea level anomalies are related by geostrophic relationship to velocity field. And here you see, and you know, the case that is most well known in the ocean is the Agulhas current region. Well, there are many other cases, but I shouldn't say it. There's also the Gulf Stream, but the Agulhas is pretty important, is the connection between the Indian Ocean and the Atlantic. And so there is, what is the mixing there? Horizontal mixing occurring, and what is the time scale by which these eddies? And you see here on the left side, yes, the image of these eddies, and you see only 3 of them, because these ones are the ones that are actual barriers. You see also contours of finite time Lyapunov exponents, but they cannot identify where are barriers to diffusion. And the next picture on your right, which is very nice. Before we go, let's wait a second. I'm trying to, yes, before we go, we see different eddies in this field. You see 2, 4, 5 eddies that, yes, let's start from the beginning, that are perfectly round. And these are virtual eddies, while these ones instead, the 3 are the same as in the other picture. So they are real eddies. And what you can see that the FTLE does not cross the real eddies, but crosses the others. And so you can but you can detect the ones that are real barriers without doing such a simulation. This is only explanatory without doing the simulation actually. So it's important to know this issue. As you will see, there are past theories on how the persistence of these eddies and their dismantling or their lifetime when they they die, at a certain point, they release concentrated tracers. And there it's the statistical distribution of tracers, the connection. So next one, please. Yes, so now we go a moment, we jump in another issue, which is in general pollution transport and hazard mapping. So we have several uncertainties, and already was presented before. We are also concerned to be able to deal with these uncertainties. So we need a probabilistic approach, and normally when you do simulations, you use ensemble simulations, perturbing the unknown parameters or using different models that have representation of different processes. But for transport, one of the major uncertainties is the representation of the flow regimes. So what we developed with the time is an ensemble approach which uses realistic flow field realizations with different and perturbed parameters in oil spill predictions. So please, next. So here it is. I'll show you the results of, we did a lot of simulations with different release points, which are release points potentially capable of releasing oil due to transport. And we did it for very, very different coastlines. We wanted to see, is it the coastline that determines the hazard of getting oil on the coast, or is it the flow field? And then, so these the three ones: South Brazil, Western Atlantic, and Eastern Atlantic. And we run several 100,000 simulations with different realization of the flow field. And what happened is, next, please.
Nadia, if you could please wrap up sometime soon, yes?
Sure. And then what we found is that we have a generic distribution representing the arrival of beached oil. And this is the framework, the generic framework that we wanted to use. So we can compare the hazard in different areas. And now we want to connect it to that barriers, because we know there is a connection for this fat tail distribution. And then next, and I conclude, I apologize for taking more time. So mesoscale boundaries can be located from velocity data as minimizer of diffusive transport without diffusive simulations. So this is George Aller method, which I tried to explain. The PDF of Ocean Tracer is a fat tail PDF indicating nonlinear accumulation of pollutants in oceanic flow field structures. And despite some advantages and disadvantages, many aspects need still to be require future investigation. Thank you very much.
Great, thank you very much, Nadia. Now I'll just check our next topic and speaker is on urban transport, and it's Catherine Gall from Stanford. I'll just check, Catherine, are you, was your connection able to work?
I think everything should be good. Yeah, power is back on. So
fantastic. Thank you so much, Catherine. So I will bring up your presentation and hand over to your good self.
Yeah, I have a lot of things to click through. So once in a while, I'll ask you to do 2 or 3 at a time. Maybe that will make it.
Sure. Are you seeing your slides now?
Yeah.
Yeah. Over to you.
Okay. So so I wrote this section together with Paul Linden from Cambridge University. And if you go to the next slide, Tom, there is, of course, a close link between urban flows and sustainable cities and communities. And it's really a really big challenge that we're facing here, because with the rate of urban migration, we would have to build a new city for 1 million people every week. So the challenge there should not be underestimated. And urban flows play a role in sustainability of cities in a variety of ways. If you can click twice, Tom. So first of all, we have wind loading on buildings, so making sure that our buildings are resilient to extreme wind events. And then secondly, there is the problem of pedestrian wind comfort and wind danger as well. So ensuring that your public spaces are comfortable and safe to use. The next two, Tom. And then we have pollutant dispersion, which is related to how do pollutants disperse through cities and what is the exchange rate with the air above the city. So how much do you flush out pollutants? We have natural ventilation of buildings, and that is of interest both for well-being and comfort, but also very much for energy savings. And then the last two, yeah, that is urban wind resources. So looking at how can we harness local wind resources in cities, and urban heat island mitigation. How do you use green spaces or blue spaces, water features in cities to try and reduce the urban heat island effect? So when you think about all of these problems, it's really not just the sustainable cities goal, but there are 3 more. So if you click 3 times, Tom, we have affordable and clean energy, which is very closely related to natural ventilation, the urban wind resources. Good health and well-being is linked to pollutant dispersion and also natural ventilation and urban heat island mitigation. And then we also have the reduced inequalities. It's well known that in cities, you often have the socioeconomically disadvantaged communities that live closer to highways, for example, and are exposed more to pollutants. So then if you would want to give these people natural ventilation, you could actually decrease their indoor air quality and create more health hazards. So if you go to the next slide, when we try to predict these flows, it's really thinking from the point of view, how can we support sustainable design? So how can we support making the right decisions? And then there are 2 main challenges in these flows. One is that there is a lot of variability in the inflow conditions, right? The larger scales that will determine the flow in the city, the weather patterns are highly variable. We have changing wind directions, changing temperatures, etc. And then the other one is that these are very complex flow problems. We're dealing with high Reynolds number, turbulent flows. So in addition, oftentimes they can be multi-physics, right? We have pollutant dispersion, we can have heat transfer problems, etc. Next one, please. So if we want to think about that uncertainty because of variability in the flow conditions, we basically have 2 options. One is we go into the field and we do measurements, and the other is that we do simulations of the larger scale. So we do weather forecasting simulation and try to couple them. So in some sense, this is really a multi-scale problem. And then the next one, please, Tom. If you think about the uncertainty because you have to use reduced order models, you can try to quantify that by doing high fidelity simulations or high fidelity laboratory experiments. And then once you've characterized all these uncertainties, you can propagate them through your system by running a larger number of deterministic simulations so that you can get predictions with confidence intervals for your quantities of interest and compare those to field measurements. And then there is something interesting that you can do at the very end. So next one, please, Tom. That is, once you have your predictions, and if you can have field measurements of these predictions as well, you can start thinking about data simulation, right? And that allows you to better characterize these uncertainties and also reduce them so that you can get more accurate predictions. And then the next 2, please, Tom. So if you think about problems like this, it's important to start from the application. What is your quantity of interest? How accurate do you really have to predict that is another really important question, right? All of that will determine how you're going to put this framework together. And that's why when we wrote the paper, we ended up focusing on presenting you 2 different case studies. The first one is done by Paul Linden. It's a consortium of UK universities. And if you're interested in what they've been doing there, you can go to the website, the MAGIC website. They've done field measurements in London, both outdoor and indoor. And they've done a lot of work on the lower square here, looking at how do you do high fidelity simulations, and then how can you build reduced order models that will be a lot faster than those simulations to do your predictions. What I'll talk about a little bit more is this top square here, uncertainty because of variability in the flow conditions, and the work that my group has done on pollutant dispersion. So next slide, please, Tom. Okay, so we've been looking at an experiment from back in 2003, the Joint Urban 2003 experiment that was done by a consortium of US universities. And they placed a source in Oklahoma City and then measured at different sensors what the concentrations were. Next one. So we built a CFD model of this, and then we looked at how can we quantify the uncertainty in the inflow boundary conditions, and we did 2 things, and you can put them both up at the same time. So the first one that we did is we looked at a field measurement that was taken upstream of our computational domain at the inflow boundary. And we looked at what the variability was and then transported that through our simulations. And that's what the plot that you see on the left here. And you see that we get pretty good predictions of these mean concentrations, right? When you compare the markers, and our confidence intervals also give a pretty good representation. So that worked very well. And then we thought, okay, what if we don't have these measurements and we want to rely on weather forecasting simulations? And that's the plot that you see on the right. And it still seems to work really well, but when you look at the scale of these plots, we actually have an order of magnitude more in our confidence intervals. And that's because we were also transporting uncertainties in the weather forecasting simulations. So this shows that it can be really interesting to use field measurements, right? So if you go to the next slide, Tom, that's what we did in an experiment on Stanford's campus. So we focused on the engineering quad here, that circle. And we decided to do two things. So you can put up both at the same time. The first one was to look at the most nearby weather station, take hourly average data and run simulations for each hour. And then the second one is the one on the right that you see here, which is we put up 6 anemometers on the engineering quad and we sampled them each with 1 hertz. And you see that for each hour, you have quite a bit of variability, right? So when you do predictions in these two ways, on the next slide, Tom, you see here are 6 anemometers, the experiments that we have hourly averaged with confidence intervals. And then the next one puts the predictions using Bayesian inference on top of that. So we use the data from sensor 2 and 3 to do the assimilation, and then we get predictions at the other 4 sensors. And when you contrast this to the next result, which shows what you get when you just do the weather station data, you see in the very bottom plot especially that you can really reduce the average error. So it really indicates that there is a lot of things that moving forward we should be able to do using data from urban sensor networks to try and improve our predictions, and also data that we measure in buildings. Right? So to conclude with the last slide here, I think for us the main challenge is really how do we put all our sources of data together? How do we use lab experiments, field measurements, high fidelity simulations? If you click on that, you'll see the fidelity that you can get in the turbulent flow representation. And then low fidelity simulations as well with all these tools, data simulation, uncertainty, quantification, machine learning, etc. And then we should get these predictions with confidence interval, but that's really not where we should stop. So if you can click one more time, Tom, then we'll be at the end. It's really important for us to think about how do we actually use these predictions to then have that impact, and that will really require working with stakeholders, the people living in the cities and the buildings, the people owning the buildings, the people operating them, etc. And oftentimes that is really the big challenge. It's not because we're going to have good predictions that we're going to have impact. So thinking about that connection moving forward, this is really important. That's all I had. Thank you.
Great, thank you very much, Catherine. And then for the final topic, before we wrap up, Peter Bauer is going to talk about the obvious grand challenge fluid dynamics problem of dealing with weather and climate. So Peter, I'll put the presentation up and over to you.
If I can chime in here for 1 second, since we're running a little bit late, please feel free to ask your questions to the speakers through private chat, so you don't have to wait until after the talk. All right, thank you.
Yeah, thanks very much for the introduction, Tom. Also, thanks very much for the opportunity to join the great list of authors here and to participate in this event. Well, in weather and climate prediction, obviously, a lot of what has been previously said, from multi-phase flows to urban scales or oceans, is coming together in weather and climate prediction, because eventually you want to have reliable prediction of what's coming tomorrow in terms of an extreme, let's say a storm as we see it right over London right now, or how extremes are changing with changing climate. We have tried to summarize this a few years ago in a paper, and we came up with this figure on the right-hand side, which is trying to summarize some of these aspects there, where on the right-hand, on the x-axis, you have spatial scales, and they pretty much align with temporal scales, because as you go to smaller processes, smaller scale processes, your time scales go smaller as well, and these processes usually evolve on shorter time scales as well. And on the y-axis, you have model complexity, which refers to, how many components of an Earth system do you actually have to account for if you want to represent, for example, turbulence at the bottom left, or interannual variability that is a La Nina phenomenon, for example, on the top right corner. As you go across scales, of course, all these factors come in. You have multiple scales, you have multiple phase fluids. The whole problem is a fluid dynamics problem in the first place, but everything matters. And as opposed to past beliefs, as if you try to describe climate at these very large scales, and like slower components and how climate change will affect the planet, you can't neglect the small scales because they're just small scales and they just add some sort of noise on top of the mean change that you're observing in global temperature, for example. We know now that, not representing those small scales well, like deep convection in the tropics or turbulence, will actually negatively affect your predictive scale in climate models. So you have an error propagation, and that's the red arrow going across in both directions. If your mean flow is wrong, your small scales and boundary conditions for downscaling problems down to urban scales will be wrong. If you misrepresent the small scales like convection turbulence and these kind of things, or exchange of energy between land surfaces in the atmosphere and the ocean, your mean signal in terms of global warming, heat waves in the future will be wrong as well. So we identified a couple of big problems where we need really breakthrough capabilities. So one relates to spatial resolution, where we say, you really have to resolve a lot of these scales because parameterizations, so approximations of small scale phenomena, are just key sources of model errors. And if you don't resolve them, you will not overcome mean errors that may only show up at climate time scales. One is, of course, the completeness of the Earth system that you represent in terms of coupling. As I said, it's a multi-phase, multi-scale problem. So you need to have dust, you need to have sea ice, you need to have, wave atmosphere interaction. You need to understand how plants and vegetation interacts with the atmosphere, and that relates to a lot of scales you have to cover. Particularly, Catherine at the end mentioned assimilation. The advantage in weather prediction is that we verify our predictions every day. We know how to use observations to assimilate, to improve our initial conditions and the predictions themselves. But of course, we have to extend this to smaller scales and multi-phase as we do extend our models to smaller scales and multi-phase. And a lot of this is actually limited by computing. And I'm going to come to that. Next slide, please. Next slide, yeah. So sustainable development goals, I guess in the case of, one back please. In the case of sustainable development goals, I guess it's fairly obvious for weather and climate, so I don't need to go through them individually. The phrase that we used in the paper relating to SDGs is what you see there represented. Of course, everything is connected. It's obvious that extremes, and we can see it in the northwest of the US and Canada right now, are really affecting mankind in many different ways. How these are going to change in terms of climate change, we don't quite know yet, but we fear for the worst. If you think of tipping points and climate trajectories that we haven't even seen yet from climate simulations, and everything relates to health, economy, environment, stress, it can cause social, political instability. So it's probably a lot more SDGs that we need to cover here. And one other aspect is increasingly you find policies and big agreements in the international context, for example, the European Green Deal, which is about carbon neutral societies. And obviously these need to be based on reliable information systems, at the core of which sits weather and climate prediction, at the core of which sits a proper representation of the Earth system, at the core of which sits proper fluid dynamics. Next slide, please. So that slide shows a couple of movies, and they all relate to simulation capabilities that we have right now already across scales. On the top left, you see a very high resolution simulation of the Arctic Ocean, including sea ice, ocean and atmosphere interactions. Bottom right, deep convection. So these are storms. Obviously, they interact with the land surface, how that scales up to the globe. So we need to represent, as I showed before, all of this. to have reliable predictions. And most of the problems that have been mentioned by the previous authors and speakers before relate to what we are trying to do in weather and climate prediction as well. And the uncertainties and unknowns that they have mentioned apply, of course, equally here as well. I should mention ensembles. I think Nadia mentioned ensembles. Weather prediction actually pioneered ensemble prediction because it pioneered chaos theory in the 1960s. So for us, the prediction of uncertainty, Catherine called it uncertainty quantification, was actually pioneered in our field and must be an integral part of what we're doing. So a proper representation of uncertainties in our models, our initial conditions, to create probability distribution functions for the important parameters that we're predicting in order to understand the uncertainties of what we're trying to convey. Last slide, please. Or second to last. I mentioned computing and data. We are running our problem on very big systems, and this is just one slide that shows you how big our computing problem is and how much it's going to be in the future. So if we think into the future, trying to run Earth system models down to a kilometer scale, so well above turbulence actually, but at least resolving the third dimension, so the vertical motions in the atmosphere, which are considered only represented in approximative ways right now, we can fill easily the biggest machines in the world. You see on the right-hand side, the top 10 of the top 500 list in computing from a year ago. So we ran one of our systems there, and we concluded that probably, on the number 10 system at that time, using the entire machine, we were an order of 100 too slow. That's one side of the medal. The other is, even if we could solve the computing problem, how do we deal with petabytes per data and extract the information that's relevant for urban city planning or climate change research? So that's a very important problem. Last slide. So the ambition that we have, which is increasingly recognized in the entire community as an extension of our Earth system simulation capabilities to very small scales. On the right-hand side, these red items there relate to 12 papers that the Royal Society just published earlier this year, leading to the COP26 conference in Glasgow, where you see exactly what I mentioned before. So very small, very high resolution, very small scale representation of Earth systems powered by exascale computing, and the notion of digital twins. It's something that Catherine showed on her second to last view graph, actually, but she didn't use the word digital twins, but which was this coming together of the entire information system of models, of data simulation as a methodology of observations to, in the end, have an interactive tool available that allows you to understand what's going on, including uncertainties, and to trial out solutions to urban city planning in her case, but in our case, up to planning dikes, planning adaptation and mitigation measures. And everything that's here in the list, I probably don't have the time to go through that, is relevant. So everything needs to be scaled up, powered by exascale computing, to the ambition eventually of digital twins of the Earth system. Thank you.
Great, many thanks, Peter. So then to wrap up, I will hand over to Claudia to provide her presentation of the summary of our work. Claudia, over to you.
So we heard several different ways in which environmental flow mechanics has a central role in help make our planet more sustainable. And to conclude, we would like to emphasize also that scientists can help societally by tackling these great challenges, but they need to collaborate, interact, and engage with experts from other fields. Catherine mentioned interact with the stakeholders and policymakers so that we can work together to identify the relevant problems to obtain our common goal to help our little planet and make it more sustainable. Next slides, please. So finally, we'd like to share some our collective thought in how we should proceed in the next decade. And we have 3 proposed action items. First, as you heard through all this presentation, we should focus and try to aim to use our research to help achieve the United Nations Sustainable Development Goals. You've seen this graph many times, and engage with policymakers so that they can make, and we can all make support informed decisions. And then another things you heard as a common thread through all these talks, we need to advance, we need to recognize that we need to advance both theoretical and numerical modeling to improve our predictions, but also experimental techniques and have, collecting data through measurement campaigns so that we can test these theoretical and numerical hypotheses and models. Next slide, please. And our last action item is like we would like to suggest 4 key topics that we believe environmental fluid mechanics can make substantial advances and can make also fundamental contribution to society for the health of our planet. So the first one is improving our understanding of coastal floods, sea level rise, and extreme weather events. That will help us contribute to more resilience planning. And here is a picture of what Hurricane Sandy did a few years ago, and I'm sure, well, I hope not, but something like that might happen as well this year. So this is a very coastal, resilience is a very important problem. Second is collection of both data, pollution transport, in order to also improve and develop new models to support mitigation of disaster, like, for example, the Deep Horizon spill, and develop long-term solution. Third is the collection of an analysis of more data in order to also, again, to improve model and prediction of the dynamic of glacier, ice sheet, and sea ice interaction, which will help us provide more constraint about the rate of this melting of ice sheets and glaciers and their impact on the environment. And finally, the design of sustainable city in the future. Since there's been this increased urbanization, so we need to think about a better way to bring all this population together and enhance human health and well-being while increasing the concentration of people in cities. So that's it. And we're all happy to take questions.
Great, thank you. I'll wrap up, just say hand over to Eckart. Obviously, it's a grand challenge to also fit so much information in 1 hour, but thanks everyone for their attention, and thanks to all the speakers. Eckart, over to you.
Yes, thank you very much to everybody. It's taken a little bit more time than we anticipated, but I think we can still take a few minutes to ask some questions. So if you have any questions, please unmute yourself and ask them right now. There were a couple of questions asked over chat, but I believe they have already all been answered over chat. So that means if there are no additional questions that are coming up right now, then we can wrap everything up here. So thanks very much. I think that was an excellent start to the week. It was great to see that quite a few of the speakers today come from countries that did well or not so well at the recent Euro 2020, and still here we're a very congenial group again. I see a big smile, especially on Claudia's face, no surprise. Yes, so thank you very much to everybody. Let me just, as a very last step, share my screen once more. And draw your attention to the new Twitter account that we have for Physical Review Fluids. So you might want to, you might want to follow that in the future. Okay, thank you so much, and have a good rest of the day. Bye-bye.
Thank you, everybody. Thank you, Eckart.
Thank you, everyone. Goodbye.
Thank you.
Thank you.
Great. Thank you, everyone.
Okay. Bye-bye.
Thank you.